Welcome to the deep dive. Today, we're peeling back the layers on energy system modeling. It's pretty specialized, quite technical,
Definitely.
but it really dictates these huge trillion-dollar roadmaps countries use to plan their climate future. We're talking about the blueprints for energy investments for, like, the next 30 years.
And that's exactly why taking a hard look at these blueprints is so crucial. The source we're digging into today offers a really sharp critique of modeling methods.
Right.
We are diving into the full title, Commentary and Critical Discussion on Decarbonizing the Chilean Electric Power System, a Prospective Analysis of Alternative Carbon Emissions Policies.
Okay, that's quite a title. But the core issue sounds fascinating. This commentary basically challenges an older study,
That's right, the Babineau et al. Paper.
which said that carbon capture and storage, CCS, was actually better, maybe cheaper even, than going for 100% renewable energy in Chile by 2050.
Yeah, that was their finding. So our mission today is to pull out the key points from this commentary. We need to detail where the original study's methods, its literature review, its cost assumptions, where they kind of fell short.
And also, what does state-of-the-art modeling actually look like now, especially for these really ambitious 100% renewable energy goals?
Exactly. What's the best practice?
Okay, let's unpack this. If you're building a study that's supposed to guide national policy, that groundwork, the literature review, it has to be solid, right?
Absolutely. It's fundamental.
So what did the original authors miss? What context was missing that makes their results, well, questionable?
Well, a comprehensive literature review is just non-negotiable in academic research. The original paper, it did cite some global 100% RE models, Europe, Japan, places like that.
Okay.
But the authors of this study, the commentary, they found a really critical omission.
Which was?
They basically failed to identify all the previous analyses that focused specifically on Chile itself.
Wait, so a major paper on Chile missed the local studies about Chile. How does that happen? Is that common, like looking globally but missing your own backyard?
It can happen, yeah, but it's a serious weakness. We're talking about at least 7 existing relevant articles on getting to 100% RE in Chile.
7. Wow.
Yeah, and importantly, these weren't just minor papers. They included detailed planning for the electricity system, sure, but also more comprehensive stuff. Studies that had already looked at integrating power, heat, transport, even desalination.
Okay, skipping that local context feels like a huge oversight. It means they couldn't benchmark their own findings, right?
Exactly.
You can't tell if your results line up with what others found for the same place or if you've actually found something new and different.
Precisely. The critique really stresses this point. You have to compare your findings to the existing literature. It shows whether your results are, in the ballpark or radically different. Without that comparison, the analysis just sort of hangs there in isolation.
Yeah, makes it hard for anyone, especially policymakers, to know how much weight to give it.
Definitely.
Okay, now let's get into the really technical part, but maybe where the biggest issues are. The model itself, the methodology. We're talking temporal resolution.
Yes, that's a key one.
What did the original study use, and why is that method seen as, like, structurally flawed for modeling grids with lots of renewables?
So the main drawback that this study points out is the low temporal resolution. The original paper basically simulated the whole future grid using just 8 typical days.
8 days?
Yeah, like a typical weekday and a typical weekend for each of the 4 seasons. 8 days to represent an entire year of complex grid operations.
That sounds incredibly limited, especially for a system running on sun and wind. Why is using just 8 typical days so bad? What do you miss?
That's the absolute core of the problem. The commentary explains this method, which is pretty outdated now. It introduces fundamental structural errors
Okay.
because it just cannot capture the 2 biggest challenges of integrating renewables, their variability and the uncertainty that comes with them.
Right, because weather isn't typical day after day.
Exactly. When you only simulate average conditions, you never see the real stress tests, the extremes.
So if the model can't see those stress tests, what happens? What are the specific consequences in the results?
Well, first, it means the model can't accurately describe how much renewable generation fluctuates. And because of that, it can't figure out the real need for flexibility, both short-term, like batteries, and long-term, like seasonal storage.
So it underestimates storage needs.
Massively underestimates them, yes. Second, and this is critical for keeping the lights on the model, completely misses climate space-time correlations.
What does that mean in simple terms?
It means you need a fully resolved hour-by-hour simulation for a whole sequential year to capture persistent weather patterns. Things like multi-week droughts where hydro dams run low, or extended periods, maybe weeks long, where there's very little wind across the whole country.
Ah, okay. So if your model only uses a typical winter day, it never experiences that 2-week deep freeze with no wind.
Yeah. That would actually drain all your batteries and maybe cause blackouts. You've basically designed a grid for average weather, guaranteeing it fails when reality hits.
That's it, precisely. If the model doesn't plan for those multi-day, multi-week low-resource periods, the whole investment strategy for storage is just fundamentally flawed.
Okay.
And third, without that hour-by-hour detail, the model can't properly quantify the real need for flexibility. It also can't model how different flexibility options like batteries versus grid upgrades versus using electric vehicles smartly compete and complement each other.
Right.
Which is why state-of-the-art modeling absolutely demands that full hourly resolution for the whole year. It's needed to capture all those complex interactions.
That makes total sense. If the model can't even see the need for flexibility because it's too zoomed out, temporally speaking, then it's obviously going to underestimate the investment needed in things like solar and storage.
Correct.
Which leads us perfectly into the next section, the costs, the techno-economic side. What was the impact of using, say, non-transparent or maybe just old cost data? Yeah, technology costs are probably the most sensitive levers in these models. The critique really emphasizes that cost assumptions must be shown clearly, transparently.
Right.
And it notes that historically, modelers often underestimate how fast renewable costs fall, especially solar PV and batteries recently.
And using old assumptions can really skew the results, right?
Totally distorts them. We can see this really starkly when we compare the recommended grid mix for Chile in 2050. Let's look at the numbers, because this is where the policy advice really starts to unravel.
Okay, lay it on us.
It's a pretty staggering gap. The original paper suggested Chile would need only about 14.1 gigawatts, GW, of solar PV. And interestingly, a pretty high amount of concentrated solar power, CSP, about 6.17 GW.
Okay, 14 GW of PV. How does that compare?
Well, you compare that to more recent rigorous studies, specifically for Chile. They consistently show solar PV as the overwhelming dominant technology.
Makes sense. Chile is famously sunny, the Atacama Desert.
Exactly. So the state-of-the-art studies show solar PV making up anywhere from 46% to sometimes over 90% of Chile's total installed capacity by 2050.
90%. Compared to the 14 GW in the original study, that sounds like a massive difference.
It is. That 14.1 GW figure looks incredibly low. It strongly suggests they were using very high, likely outdated cost assumptions for solar PV.
So how much less PV did they recommend overall compared to these other studies?
The commentary calculates it out. The original paper recommended anywhere from 2.7 times to, get this, 16 times less solar PV capacity than other detailed 100% RE studies for Chile.
16 times.
16 times, yeah. That's the difference between solar being just a small part of the mix versus being the absolute workhorse, the backbone of the entire electricity system.
And you mentioned they had a lot of concentrated solar power, CSP, that's the one with mirrors and turbines, right? Why is that significant?
Yes, that's CSP. It's significant because CSP is generally quite a bit more expensive than standard solar PV panels these days. So most current models for Chile show very little, sometimes zero, CSP being built because PV is just cheaper. The fact that the original paper relied so heavily on more expensive CST, again, points towards cost assumptions that probably didn't reflect the market realities.
Okay, so using outdated high costs for PV, maybe favoring more expensive CSP, this obviously inflates the cost of the 100% renewable scenario they modeled.
Hugely inflates it. And that has massive implications for their final conclusion, the one favoring carbon capture and storage.
Right, so what was the cost difference?
Well, because the original model used expensive renewables and, as we discussed, didn't optimize flexibility properly because of the low time resolution.
Right, the 8 days thing.
Yeah. Their resulting levelized cost of electricity, the LCOE, for the 100% RE scenario came out quite high, somewhere between 67.8 and 72.4 euros per megawatt hour.
Okay, 68 to 72 euros. And what do the newer state-of-the-art studies using current costs and hourly modeling find?
They find a dramatically lower system LCOE, usually in the range of 25.7 to 44.0 euros per megawatt hour.
Wow, that's potentially half the cost.
Or even less. So, the bottom line is, when you model it properly using current data, a 100% RE system in Chile looks like it could be substantially cheaper than sticking with fossil fuels, even with CCS tacked on.
And the critique about CCS itself,
Hmm.
it goes beyond just cost, right?
Yeah.
There's a fundamental issue with it for true decarbonization.
Absolutely. CCS is expensive, yes, but critically, even when it works perfectly, it typically only captures about 90% of the CO2 emissions from the power plant or industrial source.
Only 90%.
Around that, yeah. So it's not zero emissions. To get to actual net zero, you'd still need other likely expensive negative emissions technologies later on. Plus, major analyses, like from the IEA's World Energy Outlook, consistently find that the LCOE of fossil power with CCS is higher than almost all the main renewable options now.
And the landscape for things like hydrogen is changing fast, too.
That's another key point the study makes. Green hydrogen, made using cheap renewable electricity, is on a path to become significantly cheaper than blue hydrogen, that's hydrogen made from natural gas where you use CCS to capture some of the emissions.
Okay.
Green hydrogen is hitting cost parity way faster than older models predicted, especially in places with great renewables like Chile.
Okay, so moving beyond cost and the time resolution,
Hmm.
what other tools or sectors need to be in the model to credibly plan for 100% renewables? If you're building a grid totally dependent on the weather, you need a really diverse set of backup options, right?
You absolutely do. The market offers this whole toolbox of flexible technologies now, but the original study probably just used like one generic storage option.
Which isn't realistic.
Not at all. It drastically limits how you can optimize the system. This study emphasizes that Chile has huge unique potential that needs to be modeled specifically. Think about its existing hydropower dams, its massive geothermal potential, lots of sites for pumped hydro energy storage, PHES, plus batteries, obviously, and then the whole emerging hydrogen storage pathway.
Let's break down that flexibility piece. We hear about batteries all the time for like daily ups and downs.
Yeah, diurnal storage, covering the evening peak when the sun goes down.
Right. But why are things like pumped hydro or hydrogen so important in these 100% RE models?
Because batteries are great for hours, maybe a day or two. But for a highly renewable system, you also have to manage seasonal variation. Those persistent low wind or low sun periods we talked about, the ones that can last for weeks.
The donal flow.
Exactly. You need something that can store massive amounts of energy for long durations. That's where PHES, which is like a giant water battery using dams, and green hydrogen, which you can store in tanks or underground caverns, become absolutely essential seasonal storage solutions.
So just lumping all storage into one generic pot in the model completely misses the chance to optimize using Chile's specific geography, its mountains for PHES, its existing hydro dams.
Precisely, including diverse storage short duration like batteries and long duration seasonal options like PHES, hydro, and hydrogen is key. It adds credibility to the plan and ensures the system can actually stay reliable through low resource seasons.
Makes sense. Okay, and finally, what about widening the lens? Is just looking at the electricity sector enough anymore?
It's really becoming insufficient. State-of-the-art research has pretty decisively moved towards cross-sectoral analysis, sometimes called sector coupling, meaning you analyze the power sector, yes, but also heating and cooling, transport, and in Chile's specific case, water supply and desalination, all together as one integrated system.
Ah, so the challenge isn't just making cheap green electricity.
No, that's becoming the easy part in places like Chile.
It's getting that cheap electricity into all the other parts of the economy that use energy.
That's exactly it. The big open question now is how do you transmit that cheap electricity effectively to all energy sectors? Maybe directly through electrifying cars and heating, or indirectly by using the electricity to create green e-fuels like hydrogen or synthetic ammonia for things that are hard to electrify directly, like shipping or heavy industry.
And planning for those other sectors, like how and when millions of electric cars will charge, must feed back into how you design the power grid itself.
Absolutely. It massively impacts the electricity sector design, especially how much flexibility you need, when you need it, and the total amount of generation capacity you have to build. You can't really optimize the power sector in isolation anymore.
This has been a really crucial deep dive. It shows how these seemingly small technical details in modeling can lead to fundamentally different and potentially misleading conclusions about our energy future. Let's try to synthesize the main takeaways for modelers looking at 100% RE systems.
Okay. To really contribute meaningfully to planning for 100% RE, this study basically offers 4 key suggestions for the scientific community. First, use state-of-the-art methods. That means full hourly time resolution for a whole sequential year. No shortcuts with typical days.
Right. Capture the variability.
Second, Use transparent and up-to-date cost assumptions. Be realistic, especially about how fast solar PV and battery costs are dropping. Don't use 5-year-old data.
Okay, third.
Third, include multiple diverse flexibility options. You need short-term diurnal storage like batteries, yes, but also crucial seasonal solutions. PHES, hydrogen, optimizing existing hydro dams, model the whole toolbox.
Got it. And fourth?
And fourth, look at the energy system as a whole. Move beyond just analyzing the power sector in a silo. Include heating, transport, industry, water, perform that cross-sectoral analysis.
Okay, so hourly modeling, current costs, diverse flexibility, and whole system view.
That's the essence of it for credible 100% RE modeling.
This was a deep dive into the specific paper. Commentary and critical discussion on decarbonizing the Chilean electric power system, a prospective analysis of alternative carbon emissions policies. And it really shows quite definitively how these critical modeling choices, from ignoring local research to using outdated time resolution to using old cost data, can completely change the picture. It can make a 100% renewable future look much harder and way more expensive than it likely needs to be.
Yeah, and maybe a final thought to leave listeners with. Given that solar PV is pretty much the acknowledged champion technology in sunny places like Chile, according to the latest studies, just reflect on the scale difference here. If one older study tells policymakers they need, say, 14 gigawatt of solar,
Right.
but more rigorous up-to-date studies say the real need might be up to 16 times higher, what does that enormous gap in planning ambition actually mean for the real-world challenge? For the political will needed and the sheer speed and scope required to actually meet our global decarbonization targets on time? It's a huge difference in perception of the task ahead.